Morning, everybody. Thank you for coming to the Spark Summit. So, my name is Sim, and what I really like is software magic. That's kind of a funny thing to talk about, but software magic, the recipe for it is actually pretty simple. Right? To create magical software, you have to come up with some abstraction that matches really well to how users think about a particular problem. And then we just have this small bit of having to write the code that bridges the gap between the abstraction and whatever execution platform we're using. Spark is actually a great platform for building software magic because it is open, flexible, and quite extensible. An example of software magic with Spark is a project I open sourced earlier this year called Spark Records. If some of you are doing data engineering work or working with dirty data or complex data, if you're doing complex data transformations, in about 10 lines of code, Spark Records will give you bulletproof job execution, it will give you structured low-level logging, and it's going to give you lightning-fast root cause analysis. When things inevitably go bad, you can actually use Spark to query the errors that happened down to full nested exceptions in stack traces. But I'm not going to talk about data engineering today. I'm going to up the stack. I want to talk about how other types of users, not the really hardcore data engineers, consume data with Spark. As you heard, Swoop is in the advertising space, which means that we deal with lots of data. And we do both analytics as well as machine learning and AI on that. What's unique about an advertising business is many people in the business have to work with data, down from people who are fresh out of college, not even data scientists, business users. And so we take pride in having created a really powerful data-powered culture. What does that mean? That means that pretty much anybody at Swoop can ask a question that's about data or about insight and get answers very quickly and cheaply. People feel empowered to expect that questions are answerable. And so to do this, to enable a data-powered culture, you have to be able to do ad hoc analytics very easily, as well as machine learning and AI. And what's unique about the data production needs of data-powered culture as opposed to the traditional ways we use data in the enterprise is that we have substantially new types of users. We have business users who not only consume but also produce data. And we have data scientists who both consume and produce data. At Swoop, any spreadsheet that a business user creates can actually be added to the Spark data lake. We use Google Apps, Google Spreadsheets to Google BigQuery to Spark. And data scientists spend more than 80% of their time basically data munching. Anytime a data scientist samples data, they create a new data table. Anytime they do feature engineering, they're effectively doing schema changes. Add a feature is like adding a column, removing a feature is like removing a column, changing its type, etc. I call Agile data production the combination of tools and technologies we need to enable a data-powered culture in the enterprise, to deal very rapidly with new data sources, new schema, and new query types, things we haven't seen before. And what I'll try to convince you in the rest of this presentation is the traditional approach to dealing with data in the enterprise, be that with Spark or be that with traditional tools, whether we use native SQL or some fancy DSL like Spark DSL or the traditional dozens and dozens of BI tools, are actually terribly suited for Agile data production. And we need a new abstraction, which I call goal-based data production, that I think can work very, very nicely on top of Spark to address this issue. So let's look at an example to motivate the use case. So this is a classic ad hoc query that a business user at Swoop might have. So let's kind of parse it and understand what it means. So top 10 campaigns by gross revenue means top 10 campaigns by the amount of money that advertisers paid Swoop. Running on health sites means running on sites whose site ID happens to be in the health industry vertical. Weekly for the past 2 complete weeks is self-explanatory. Cost per click is gross revenue divided by the number of times somebody clicked on an ad. And click-through rate is the number of times somebody clicked on an ad divided by the number of ad impressions, the number of times somebody saw an ad. So pretty straightforward. Business users want to see something like this. The first column is a date with the beginning of the week. The second column is rank. The third column is the campaign name, which I've sanitized to protect our clients. Third column is gross revenue, in our case in dollars. The third column, so the cost per click and the CTR. And a couple interesting things to notice there, that for humans, we often want to consume ratios as percentages. And we probably don't want to see 12 digits after the decimal point, right? Machines don't care. In fact, you don't want to round and reduce precision for machines, but for humans, you do, because it helps us grasp data better. Don't read this. It's not meant to be read, but this is the Spark SQL it takes to produce this data. It's only this short because I actually created a support ticket and asked Databricks for help to help me figure out how to do beginning of week calculations in a manner that was shorter than what Google helped me do. So you have to do a couple joins, one of the dimension related to sites to bring in the industry vertical based on a site ID. You have to do another join to bring in a human readable campaign name based on a campaign ID. You have to use window functions to compute rank, and you have to have some pretty gnarly expressions to do things at a weekly level of granularity. A Spark DSL, be it Python or Scala or R, won't help us. The reason why it won't help us is because its abstractions are essentially SQL level abstractions. Filter, group by, sort. So what we have here is a classic abstraction gap. The way we as humans think about data, or at least the non-data engineers among us, certainly business users and data scientists, is very, very different than the way databases or Spark think about data. Right? And the reason is SQL. SQL was created in the early 70s. Back then, there wasn't much data. Data changed extremely infrequently. The people who work with data were very few, and they were very different than the people in the rest of the enterprise. But that's not the world we live in now. We actually want data-powered culture. We want an enterprise where anybody can consume data, almost anybody can produce data, and we can deal with very rapid evolution of data sources, schema, and query types. Well, we have some approaches to make SQL more usable. We can use BI tools. We can build views upon views upon views. We can use, in a Spark ecosystem, user-defined functions of various complexities. In some other traditional databases, store procedures. None of these things help. Right? When a data scientist is doing feature engineering, they may be, quote unquote, changing a schema or producing new data sources many times per hour. Do you know of a business intelligence tool that can deal with new data sources and schema changes many times per hour that a data scientist can use quickly? I don't. Yes, we can set up views to make almost any type of query easier, but we have to know the query ahead of time, right? Plus, just think about how many meetings it takes to add a new data source or a new view to the sort of enterprise-blessed data warehouse. So that doesn't work. In UDFs, data scientists actually use user-defined functions a lot, but really simple ones. Complicated ones, or complicated store procedures require the trained engineer to build. So that doesn't work. So what we need is something else. But before we understand what we need, it's important to understand the root cause of the problem. The root cause of the problem is that the abstraction gap is actually a generality gap. See, Spark is a general-purpose data processing platform. That's supposed to be its greatest strength, and it is. It also happens to be its greatest weakness. A general-purpose data processing platform cannot make any assumptions about the data it's working with. Because it cannot make any assumptions about the data it's working with, it needs to be told every last nitty-gritty bit of everything it needs to do with the data. It needs to be told that weeks start on Monday. It needs to be told that the data in the database is a universal time coordinate. It needs to be told that the reporting time zone is US Eastern. And all those things, right? So Spark needs not just the what we want the result to be, but also the how to produce it. So here I took one of the production examples of the code, and I just colored every single character related to what we wanted the result to be blue, and every other character red. And it turns out that 95% of the characters we used to produce the data related to how we wanted the data production to run. It was the explicit context. And that actually happens to be true. I encourage you to go back to some of the queries you use in your enterprise in whatever environment, SQL, some DSL, and just go through this exercise. And you'll find that only between 5 and 10% of the key presses you do relate to the result of what you want to get. And the rest is just the mechanics of how to get it. That on the surface may be just, well, that's life. But actually there's some really serious problems with it. The first one is that in addition to verbosity, we have a lot of repetition. Our code is not dry, so we violated the don't repeat yourself principle. See, things like calculated columns need to be computed at the last layer of aggregation, so they're very difficult to add in views, or very difficult to add in views that you may want to aggregate over. So what ends up happening is we type expressions like the above, where we calculate a click-through rate over and over and over again, or type formatting over and over and over again. Anytime we want to get a readable campaign name, we have to join a campaigns table. Anytime we want to get a site vertical, unless we denormalize the data up front, we need to join a site table. And last but not least, we end up with very inflexible code. So here's the expression that is actually used to calculate the beginning of a week. So you need to know the name of the column. You need to know the data type of the column. In this case, it's a millisecond timestamp since epoch start, 1970, January 1st. You need to know the time zone of the timestamps in the database. It's not always UTC. You need to know when do weeks start. For us, I live in Boston, it's Monday. Some other people in the US, their weeks start on Sunday. In the Middle East, they often start on Saturday. And you also need to know the reporting time zone. If any one of these things changes, this code is going to have to change. If you wrap this in a user-defined function, you have to parameterize it by 5 things. That's not really helping much. This generality over time creates massive amounts of technical debt. Those of you who were here yesterday saw the Databricks keynotes referring to a Google paper about the technical debt associated with machine learning and data production, saying that this type of ad hoc query done on its own without any framework to help and reduce the verbosity, reduce the inflexibility, reduce the amount of repetition, over time gets you in a very, very bad place. So if you're starting to use Spark now, it may feel very, very productive. And you're just banging it out. You use reuse by cut and paste, and it's great. 2 years from now, it's going to get bad. Like barnacles on the hull of the racing boat, this type of technical debt is going to build up, is going to keep adding friction to your data production. As you change things, as you change schema, things that used to run are going to fall. You're going to have to change them. You're not going to know what's going to fail. And it's going to be a problem. So we need a way to solve this. And to me, the approach that works is what I call goal-based data production. The trick to goal-based data production is that it expresses the solution to the problem the way humans look at it. It wants to be magical. So we only want to use directly the information about what we want the result to be. And then we somehow magically are going to provide the how via generative just-in-time context. So it may look something like this. Don't worry about the DSL. Don't worry about the specific methods and things. That's less important. But this reads about the way the data production requests read in English. It makes sense. I've shown this to many, many business users who are technical enough to maybe use complex Excel formula or maybe write the occasional Excel macro. They go, yeah, sure, I can understand that. That makes sense to me. I can write that. So the obvious question is, does this run? What can you do with it? Well, let's see about that. So there it is. I'm in a Databricks notebook. This is Scala, and Spark is back. So let's just run this. I made it in lazy value so it doesn't output a bunch of internals about the data structure. And let's just try to display it. Okay, except it's actually a decent amount of data that it needs to go through. And there it is. Exactly what we wanted to see. And then if I just take a peek and say, hey, how did you figure this out? You'll see some interesting things. And I don't want to go into the details of it, but you'll see, for example, that it's using daily campaigns report. If you recall, neither the data production request nor the human description actually mentioned the data source. That's because we as humans don't care where the data comes from. We just care for it to be accurate for what we want the production request to be. And the rest is essentially how the goal-based data production system figured out what it needed to do automatically. So how does that actually work? Again, don't worry about the DSL. I want to talk about the underlying processing and configuration models that enable this and potentially any other DSL to be built. Just like SQL enabled the Spark DSL to be built, and Python and R and so on and so forth to be built. So data production requests has any number of data production goals, and goals can be associated with one or more data production rules. An example production goal may be to have a column called CPC. We may not know how to produce it, but we know that we can't satisfy the data production request unless we figure out how to create a column called CPC. An example rule is that we need to filter data to the past 2 complete weeks. Rules are associated with requirements. For example, if you're going to do a time filter, some column needs to be a time dimension column. I may not know its name, I may not know its data type, but I can't filter by time unless I know which column to filter on. If I need to filter filter to complete weeks, I need to know when does the week start, what's the time zone of whatever time dimension column is in the data, and what time zone am I reporting in. So context gives us metadata that allows us to resolve the requirements and thus turn unknowns into knowns. As we turn unknowns into knowns, we can rewrite the data production rules, effectively doing the equivalent of variable substitution. As we keep doing that, eventually, we either run out of things we can resolve, at which point we generate some meaningful error, or we fully resolve all the data production rules, at which point we can actually produce a Spark dataset. We're done. The key is how do we provide this context, because it's the thing that enables the magic. Traditionally, in the enterprise world, we have done this using the sort of holy grail one version of truth way. It goes like this. We sit in meetings for 6 months, preferably 4+ hours a day, and argue about what the schema should be and what the views upon views upon views we're going to build. And then we agree on something, and then for the next 3 years, we are unhappy about the fact that we didn't quite get what we wanted because we had to compromise with some other group on the one version of truth. In an enterprise where there's so much data and there's so much new data, expecting to have one version of truth is just silly. Yes, maybe that's okay for sort of the transactional, hardcore operational systems, but it makes absolutely no sense for data related to data science, especially exploratory work, and ad hoc queries by business users. What we need is a way to provide just the right amount of context to satisfy a data production request. And it's very common that 2 data scientists, in their own work in the moment, may use 2 features that are named the same thing, but actually different things. Do they need to not do that? Should we tell them, hey guys, you didn't know this, but this thing called X that is the same for both of you is actually different things. So you need to go and have a meeting and agree which one is going to call one X1 and the other one X2 and then change a bunch of code. Well, it makes no sense. It only makes sense to do that if the work goes past exploratory to some way to be shared across the team or to be shared in the rest of the enterprise. So this need to sync up and create unique things way too early in the data production process is completely wasteful. So you actually want there to be conflicts. You just want to not be able to fail because of conflicts. So think of context as a query over some set of metadata. And you can combine production-ready context, like in this case, some, let's say, release of metadata, combined with, maybe my personal workflow doing some machine learning experiments right now. Or if I'm collaborating with another data scientist, they can tell me, hey, my stuff is tagged this way. So that's how you can get the latest that I'm working on and maybe sort of see the thing observed in this particular data production request. You can reproduce my result. We talk about context being generative. In a typical BI system, if you have 2 tables, you can say, hey, the way, dear BI system, you can join these tables is like this. If a data scientist samples a table, they'll create another data source with the same schema. I know of no BI tool which will automatically allow the data scientist to do some visualization on that new table, which happens to have the same schema. So we want context to be based on, not on specific tables, but on tables satisfying certain requirements. In this case, we can say, hey, any table which has a column called campaign_ID can be joined to a campaign's dimension so that you can get a human-readable campaign name and whatever else, right? That makes sense. Yeah, but why restrict it to column names? For example, at Swoop, campaign IDs can live in 4 different column names based on data structure, data type, mixed case, lowercase, etc. So you can actually have a generative rule which says, hey, forget the column name. As long as the values in the column are Swoop campaign IDs, you can join them to the campaign's dimensions table completely automatically. We can do the same thing for calculated fields. Right? In this case, the expression is actually a Spark SQL expression. Spark SQL expression is actually parsable, they're a tree. So you can inspect this code and figure out that it depends on a clicks column and a views column. So this basically means, hey, any table which has a clicks or a views column, in this case there's no restriction on their semantics, which we probably want to add in a production system, can actually have a column called CTR, which is calculated like this. We can do humanization formatting, including changing the data type and changing the column name. In this case, formatting the click-through rate as a percentage, reducing its precision when we want to show this to humans. And that's what the .humanize did in the data production request. If we're doing data generation to using machines for machine learning, we wouldn't humanize. But if we're showing something to humans, we usually would sort and format the data. Sorting in particular is very expensive in Spark, because if you want universal sorting, you're streaming everything for a single worker. So you're actually really, really slowing down your data production request. So you only want to do this if a human's going to look at the results or you care the output to be sorted. You can also do optimization. You can provide metadata that tells about certain data properties, uniqueness or relation to primary keys, and so on and so forth, which allows query plans to be rewritten in a more optimal manner. Classic optimization is to do joins after you reduce the number of roles for an aggregation, as opposed to before you perform an aggregation. And you can do this if you know that the relationship of some column is one-to-one with a primary key. Since campaign names are unique, rather than grouping on campaign name, you can group on campaign ID, join campaigns after the grouping. You run many times faster. Smart databases do that today. Spark does not. Again, because it's a general purpose platform, it does not require the strong sort of schema and model of, say, an Oracle database. Its optimizer is somewhat limited. But as we come up with smarter data stores for Spark, like, for example, Databricks Delta, which was announced yesterday, which calculate execution statistics just like many enterprise databases do, then you suddenly start having access to metadata like that. So you may not even have to manually specify hints like this one. So this is the magic that allows us to do automatic source detection. At Swoop, not counting any ad hoc data sources that data scientists created, there are at least 14 materialized data sets that can satisfy the example data production request. 2 of them are good choices. Which one depends on sort of the phase of the moon. They're just about equivalent. And the worst one will probably run 3 + 100 times slower than a fast one. The average one will run probably about 100 times slower. We can do joins automatically. If we know we need to produce some column and it depends on some other columns and they're not in the source table that we've identified, then we can look at a path. Can we reach this column or its dependencies in other joins? And then we can use cost-based join optimization to actually produce a total plan that's equivalent, or in some cases better, than a hand-coded plan. All this leads to a really flexible way of working with data. And if we don't have the context we need, you can provide it just in time, just right after you see an error. You can provide it and persist it and tag it appropriately to you or your use case. And then over time, we can promote context that is useful up to our team, beyond our team, and so on and so forth. The net result is that we can do data production at least 10 times easier because we're saving 10 to 20 times the code. And that just in the moment we write it. We also don't have the problems we talked about before. Our code is dry, it's much more flexible. If we change the metadata, things change, right? And the best part is that we just say to data frame or to data set, to DS, and we end up with a Spark data frame or data set. So this is perfectly interoperable with the way we use Spark. The net result is really a revolutionary change in how we think about data. First, we enable business users, and I don't mean sophisticated business analysts. I'm talking about, the person who's comfortable working with a complex Excel spreadsheet. And we enable data scientists, even junior ones, to do much, much more advanced exploration, data production for their own needs. Data production speeds up, costs go down, performance goes up, execution costs go down. And their collaboration benefits. And that's why, to me, this technology enables culture. It enables an empowerment in the enterprise of people believing that the question is actually answerable. While in a traditional enterprise, people learn helplessness. Oh, I have a question. I may be able to answer it if I send an email and then wait for 2 days for whoever asked the favor of answering it for me. But I can't get an answer now. And that's how we make worse decisions. And that's, to me, is the fundamental benefit of goal-based data production. It enables enterprises to make better decisions all the way down the hierarchy. At Swoop, we use bits and pieces of this, and we actually want to open source it. So if you want to help out, this is interesting. If you think you can use it, reach out and see if you want to help. This is all that I wanted to talk about. I'd love to take some questions.
If you guys have any questions, you can please step up to any of the 2 mics.
Hi.
Hi.
Thanks for the great talk. You mentioned definition, the past to we complete definition. Where does that definition lives? How is it created? And how do people know about that definition? Because I think there's a difference between the past 2 weeks and the past 2 complete weeks. And that can be quite important. How does that work?
So it's a good question. Did everybody hear the question? See, there were some essentially human bits and pieces of language that were parsable. So a number of BI tools use filtering language like that. So Looker, for example, has an advanced almost free-form way of specifying date filters, which are very common. There are code libraries that will let you do that in Ruby and in Java. Google Calendar lets you do it. So it's no different than these problems, right? You pick up some limited form of grammar and natural language processing, and then you need to teach the people, just like you teach people how they can specify dates in Google Calendar or using Looker. And then write the code to map the abstraction to an underlying data model that actually precisely describes what the thing means.
Yeah. Thanks.
Any other questions?
I have one.
Yes.
I'm wondering, at what stage in your pipelines do you deal with all the messiness in the data? For example, you're working in ads, so you should have only one inventory ID, but sometimes it gets duplicated. And all of this is based on the fact that the semantics of the tables are enforced. So at what stage should you do that?
So the question is about semantics and enforcing semantics. So there was a question, then there was an assumption going with the question. I'll answer the question, but the assumption is also incorrect, right? So because we're in advertising, most of our raw data comes from essentially a public API. And we see all kinds of things. We see hackers just probing around. We see garbage getting sent. We see bizarre, strange JavaScript environments. They set floating point timestamps. In one sample of several billion events, there was one which had a client timestamp from the browser that was a floating point value. So we handle this actually with Spark records at the point in which we turn our incoming raw events into sort of a curated, verified Parquet schema. The assumption that went with your question was that how do you enforce the semantic? Because the semantics matter. The semantics matter for any one, let's call it data frame or data set. I want to use the Spark terminology because I don't care what sits behind it, right? But CPC could actually mean multiple different things in the entire set of metadata that constitutes context. It has to mean only one thing if you're going to use CPC in one particular data production request. So then it's your responsibility to set up your context correctly. Now, the system can tell you, hey, you're asking for CPC, actually see more than one definition. Here they are. You probably didn't set up your context environment correctly, and you need to do that. Or you need to tell me which of the two I should use. But as long as there's only one, the system will proceed. And if you have made a mistake in the selection, then it will produce, somewhat strange results. That's why you can have permissions on context, you can have blessed production one, as well as experimental one.
Okay, thank you. Last question, and then we'll close out.
Yeah, so I had an impression that when you were showing the joins, they are often, at least from the examples that you shown, that they are often at a small data level already. Like campaign ID, you will not have billions of campaigns, I guess. So, but this is running on Spark, I imagine. So how does this compare to tools, let's say, like Tableau, where it could consume already the output of Spark, where you could easily join in campaign IDs and so on? And why did you go for this approach?
Also, just to be clear, right, the underlying execution engine is Spark. So this is just an abstraction layer over the Spark DSL, or actually both Spark SQL and the various language DSLs. Their underlying representation is actually a logical plan operator. It's a Scala case class. It's just a tree of operations you perform. Filter the data, group it, query it, roll it up, etc. And so the actual execution of a join, be it a small or a big one, is up to Spark. What you can provide is you can provide execution hints to speed it up. So for example, if it's a small table, you can say, hey, this is I'll give you a broadcast hint, right? If it's a big table or it's an unknown table, you let the Spark optimizer do the best it can. Again, if using a smarter data environment, like say Databricks Delta, or if you happen to be using Spark to query an enterprise, relational database, then a lot of the information is going to get pushed down to the underlying source, and its smarts can kick in. If you're using a dumb representation, native open source Spark against, say, files on S3 or HDFS, Spark Optimizer is still fairly mature, but it's going to get better over time. Thank you so much.
All right, thank you. Give Sam a round.